Now, chemicals, of course, contain chemical energy. So in this next section, we are going to discuss how energy tends to change and how it tends to flow from reactants towards products within a chemical reaction. The Gibbs free energy equation is a mathematical model that helps us track the flow of energy through chemical reactions. It's helpful in determining which type of reaction we're dealing with, and also whether those reactions release useful energy or capture useful energy. Let's take a look at the variables involved in this equation. First, we have delta G. Delta G is what we're calculating, and delta G represents the change in free energy as this chemical reaction proceeds. Now, free energy is the useful energy. It's the energy that is available to do work. So it's the forms of energy that can make chemicals react, that kind of a thing. On this side of the equation, we have the delta H. Delta H represents something called enthalpy. And enthalpy is the total amount of energy present in all of its forms, both useful and not useful, in the system. T is going to simply represent temperature. And the delta S is going to represent the change in entropy that we see as this reaction proceeds. So it keeps track of whether we're going from an ordered state to a disordered state or vice versa. Next, let's discuss what's going on mathematically with this equation when we change each of these variables. In other words, how do changes in each of these variables affect the amount of free energy we have in a system after a chemical reaction has occurred? First, let's consider enthalpy, the total amount of energy. If the total amount of energy present is pretty high, then it's also fairly likely that the amount of free energy will be high. And if the amount of total energy is really low, if there's not much energy present to begin with, then your amount of free energy is going to probably be pretty low in that chemical reaction. However, this can be affected quite a bit by these two guys. You have to take these into account as well, temperature and entropy. Notice that we are subtracting from our total the product of temperature and entropy, the level of order to disorder. So what that means is that any increases in temperature and or entropy is going to tend to decrease the amount of useful energy overall. And the reverse is also true. Any decreases in temperature and or the level of entropy are going to tend to increase the amount of free energy left in that system. The Gibbs free energy equation can help us determine which type of reaction we're dealing with, whether it's spontaneous or non-spontaneous. A spontaneous reaction can happen all on its own. In other words, it does not require a large input of energy to get started and to proceed. Now, all reactions require a little energetic nudge to get started. That's something called activation energy, which we'll talk about in a moment. But a spontaneous reaction is going to release energy. It does not capture energy. So you don't have to put any more energy into the system to really get it rolling. It can happen all on its own. Now note that the word spontaneous does not mean fast. Spontaneous reactions don't always occur quickly. This just means that they can occur energetically on their own. Let's consider this reaction. The breakdown of glucose into these smaller molecules CO2 and H2O. We begin with one large molecule, very energy dense, and what we end up with are a bunch of little molecules, each of which only contain a little bit of free energy. So what's happened here? Well, you can see entropy in progress. The big molecule that's very organized is broken down into a bunch of little molecules, each of which are less organized than the original. So what does that tell us? Well, on our equation, that means that our entropy number is going to be really, really high. And what we end up with when we calculate the delta G for this reaction is a negative number. In fact, the actual number is negative 686 kilocalories per mole for this reaction. So what does that tell us? A negative delta G means that the reaction is going to be spontaneous. Another way to think of it is that when this molecule is broken down into smaller units, energy is going to be released. Free energy is now available that can do work. This is the reaction that we use to power most of our other chemical reactions. When we break down glucose and burn glucose through metabolic reactions, we release energy. And what do? Well, we have CO2 and H2O as a byproduct. We breathe out the CO2 as a waste product. And this provides the energy we need to do other chemical reactions. Some reactions are non-spontaneous, meaning that they do require an input of energy to proceed from reactants to products. In other words, these reactions absorb energy, and because they need energy, because they absorb energy, they're not going to happen randomly on their own. That's why we refer to them as non-spontaneous reactions. Let's take a look at an example. You'll notice that this reaction is the reverse of the one on the previous slide. Here we're going to take little subunits, such as CO2 and H2O, and combine them into one big organized glucose molecule. Now, obviously, it's going to take an input of energy to do this, because you're going to have to force these molecules to get together and to make this one big subunit. So what's happening energetically here? Well, the amount of entropy in this reaction is going to be very low because we're going from disordered to a more ordered state. And that means that the level of free energy is actually going to be fairly high. In fact, you're going to end up with a positive free energy for a non-spontaneous reaction. If we look at the actual delta G for this reaction, it is a positive number. It's 686 kilocalories per mole. That means that that amount of energy is captured in the glucose molecule as the reaction proceeds. So why do chemical reactions need activation energy? Well, think of it this way. If we have these little molecules and we want them to react with one another, they're going to have to physically hit together. And they're going to have to smack together with enough physical force to actually react, to overcome their natural repulsion of one another. So by adding energy to the system, we say that we bring these molecules into the transition state. The transition state is actually a fairly unstable state, but at this point, the molecules have the maximum potential energy. They have the most potential to react with one another. If they're moving with sufficient speed, they can hit together in the right orientation and react and produce the products. Next, we'll discuss different types of chemical reactions that we'll see in action inside living cells. Now, there are many different categories of chemical reactions out there. For our purposes, we're going to think of reactions as fitting into two categories: building reactions that capture energy and breaking reactions that release energy. This first category includes reactions that break molecules and release energy. Molecules that release energy are called exergonic. Think of the energy exiting the system. Reactions that break molecules, rather, are called catabolic reactions. To remember that term, I think about my cat knocking stuff off of my shelves and breaking it, because cats are kind of jerks and they like to do that. So a catabolic reaction breaks molecules. Here we have the example that we were looking at before, where we take glucose and we break it down into carbon dioxide and water. We take a big molecule and break it into small molecules. When that happens, energy is going to be released, and we consider that an exergonic reaction. This line graph represents the progression of an exergonic reaction. So here again, we're going to start with glucose. Now, glucose has a certain amount of energy, so it's sort of high on this y-axis. Notice that as the reaction begins, there's a bump. This bump is the energy of activation. That's the energy that has to be added to the system to get this reaction going. Once the energy of activation has been accomplished, the reaction can proceed, and notice that the products of this reaction have less energy than the reactants that we started with. So energy was released through this system, making the reaction exergonic. Now, endergonic or anabolic reactions build molecules and capture energy. The endergonic part refers to the capture of energy, so imagine energy going into the system and being captured. And anabolic refers to the building of molecules. Here's an example. If we take CO2 and water and we add enough energy to it, we can build it into a molecule of glucose. One molecule of glucose is quite a bit bigger than these little molecules of CO2 and water that we started with. So the energy that's been added to the system has been captured inside this glucose molecule. That's an endergonic reaction. Different chemical reactions used by cells are going to either release or absorb different amounts of energy depending on the type of reaction that we're dealing with. Here's an example. You can take glucose and you can actually set glucose on fire. Sugar will burn, believe it or not. We'd call that a combustion reaction. Now, if we set glucose on fire, it's going to release a lot of energy all at once. That's the heat and the light of the flame that you see. That's not super useful for living cells. For one thing, cells would set themselves on fire if they started trying to combust their glucose. Also, because all the energy is released at once, it makes it hard to capture and hard to deal with. So living cells tend to have a different approach. When they release energy, for instance, they will do it in a series of steps. So they might break glucose down a little bit, get some energy out, break it down a little bit more, get some more energy out. They get all these little bits of energy out of glucose one step at a time through a series of smaller reactions, and that allows them to capture a larger amount overall. Living cells will often put exergonic and endergonic reactions together to make the products that they need. Let's say, for instance, that we actually want to make this little product. We're calling it H. In order to make H, we have to perform this reaction, and that requires energy. Now, where can we get this energy? Well, maybe we can use this reaction to power it. This reaction is exergonic because it releases energy, and then that energy can be used to power the bottom reaction, which is endergonic. When this occurs, we refer to this as a coupled reaction, and cells use coupled reactions all the time. They use exergonic reactions to release energy that can then be used to build something that they want to make. This simple diagram contains an example of a coupled reaction. So for this your turn, I would like you to examine this diagram and tell me where you think the endergonic part is and where you think the exergonic part is. Notice that one reaction is powering the other reaction.